Hello, calculus class. Here's the loose end from whatever day this is, Monday and Tuesday. What did we do in class? Too much is the answer. We really needed 90 minutes. We had 55 and we kind of failed. Possibly I rushed everything so much that you learned nothing. So you're going to have to put some effort in to go back and look over these things. In the first 10 minutes of class or so, we looked back at the calculus of implicitly defined curves. So y squared equals x cubed, not a function, but it is a curve. And we can not only compute dy dx, which tells us the slope of the tangent line to the curve, but we can also ask deeper questions like, at what rate is the slope of the tangent line changing? That requires us to look at the rate of change of dy dx, and that's exactly what we do. We take the derivative with respect to x of dy dx. And it's important to realize that this is the derivative with respect to x, because what we're really asking when we ask for, so there's this, this is just a reviewing class a little bit, hopefully this won't take too long, but this thing here in yellow, you have to really understand what this means. What this means is, thinking of dy dx as a formula, in fact it is, and something which is changing at different points on the curve, there will be different slopes. The derivative with respect to x of that is asking, for a small change in x, what is the slope doing? And we found that by using the dy dx, we can differentiate this again with respect to x. We get a complicated formula, and after multiple algebraic simplifications, it gets to be a little bit easier. What is this? It's the rate at which the derivative is changing, you might say. And you can take any point on this curve, and indeed we showed that for any point in the first quadrant, this expression will be positive, which means that the slope of the tangent line is increasing. Okay. Great. Which means that this curve is concave up and this curve is concave down. Okay. Then we introduced the calculus of parametric curves. Parametric curves are really important because, in fact, someone even asked live in period 4, why is this important? And I was in a rush, so blew them off a little bit. But, of course, after class I answered that we have been studying motion in one direction. But, of course, motion doesn't usually happen in one direction. It happens in two directions. And so if you have some kind of object moving around in a two-dimensional space, then you would describe their motion parametrically. You would have one formula for the x position with respect to time and another formula for the y position with respect to time. So in fact, parametric curves are really important for analyzing motion as soon as you leave the special kind of toy case of motion in just along a one-dimensional line. Okay, and even back when we did parametric equations back in November, we talked about how the thing that motivated the study of parametric equations was the fact that if an object is falling and you are thinking of that object moving in a two-dimensional space where one of the directions is up and one of them is kind of side to side, then of course there are totally different forces governing an object which is falling versus an object which is moving horizontally. One is subject to gravity and the other one kind of isn't in that direction. Therefore, it's completely reasonable to describe those objects with a pair of parametric equations. And so we're not going to do so much of this in this class, but in physics you will absolutely analyze things parametrically, very often. Okay, back to the calculus. We reviewed. This whole video is going to be kind of like a review or something. We talked about how an object is moving along a curve. This is just an example of a very complicated curve. And calculus can help us learn what's going on. And at any given point on that curve, at any given time, t, we may ask, what's the slope of the tangent line to the curve at that point? And just like with regular derivatives, remember there was that one day, hopefully this resonated with you maybe in late February, early March, where I said that you should think of the tangent line to the curve as the path that the object would take if at that moment you removed all forces on that object. And so, in fact, the slope of the tangent line to the curve is the instantaneous velocity vector in some sense. It's the velocity vector because x is moving, y is moving, and at that moment, the tangent line is telling you what the curve would do if you sort of let go of the string on the object and just let it go, continue going straight. So you should think of this this slope as really being, if this is a position, if this is a, I'm getting a little bit off subject here, and maybe this will be something for another day. But here I'm presenting this as kind of a math problem. But if you instead present this as a position problem, oh man. I don't know why that would be happening. Come on, Google Jamboard. Why can't we sync our changes? Let's try that again. So in other words, here I'm just saying, hey, here's an equation, here's an equation. But if you wanted to be more physics about it, what's really happening, perhaps, is that you have a position vector. And that position vector has two equations. There is the, well, I guess I should stick to my same notation here. There is the, you plug a time input into this, and what you get back is one function which described at any given moment where the x-coordinate is, and another function which described at any given moment where the y-coordinate is. And so the output of this position function is in fact like an ordered pair, x comma y. That's kind of another equivalent way. These are two ways of saying the same thing. And if that's the case, then the slope of the tangent line is in fact like the velocity vector or something like that. The direction that the tangent line is pointing in is the direction of the velocity vector, at least. Okay, more on that later. Anyway, so that's why you should care about dy dx to a parametric curve. How do we actually compute dy dx to a parametric curve? In period 3, I went on a long-winded explanation that was like too rushed to be helpful, so I apologize for that. But in period 4, I think I just skipped right to it and said, look, man, if I want dy dx is just dy dt over dx dt. Why? I gave a long-winded kind of explanation, which was actually fun and interesting, but it was too rushed to be helpful. Maybe the simplest thing to do is just to recognize this as just the chain rule. The chain rule says that the derivative of y with respect to t is the derivative of y with respect to x times the derivative of x with respect to t. So the chain rule says that derivatives just act like fractions, and so you can just cancel dx from the top and the bottom. That's what this is the chain rule here in the box. And so if I just divide by both sides by dx dt, I get this formula. Okay, if you understand that, good. Then we did this big example. I'm not going to go through the details again, but essentially we took a pair of parametric equations describing a curve C. We looked at the end behavior of that curve in both directions. This is pre-calc stuff. We then saw that the y function is just a cubic polynomial which can be factored, and we can therefore make a sign chart for x and y. Then we used our calculus knowledge and we computed dy dx by differentiating y with respect to t and differentiating x with respect to t, and then we got a formula. And you should, I don't know if I paused in class enough to really drive this point home, but what we really have here is a formula for dy dx in terms of t. So you plug in a time or you plug in a t value, and this function outputs what the slope of the tangent line to the curve is there, which we can interpret as the direction of the velocity vector. Okay, anyway, it seems like something important is happening at root 3 and negative root 3, so I plugged those t values in particular into this formula, and I got the slope of the tangent line to the curve at those times. And then also, when do I have a horizontal tangent? When the numerator is 0. When do I have a vertical tangent? When the denominator is 0. Okay, I'm spending a lot of time just reviewing, but maybe that's good. So, plugging those five t values into this curve, because these are the 5 t values of interest. At 0, they're both 0. At root 3 and negative root 3 is when the curve passes back through this point 3 comma 0. And now you almost can't see it, but these green lines here are meant to indicate the slope there. And at t equals 1 and negative 1 is where we have horizontal tangents. So I draw those points in. And by using this sign chart, by using the fact that I have a vertical tangent at t equals 0 and a horizontal tangent at t equals root 3 and at t equals -1 and at t equals 1, I kind of know everything I need to know to be able to sketch this curve. Now, I've made some assumptions, and I in order to just finish the problem, I just did do the sketch, and this sketch is right. But of course, there is one more piece of analysis that we could perform here, and that is we could determine the concavity of this kind of fish-shaped thing. So, all right, the last thing I want to do, and in period 4 I mentioned, I made a kind of a sad face because we just had no time, that I would like to compute the concavity. And if I want to compute the concavity of this curve, then what I really need to do is to compute the rate of change of the derivative. All right, so it's difficult enough already just to even realize that that is the thing that I want. But what I want is this, is this d squared y dx squared thing, which this notation is really, I find it distracting and students don't like it. So the best thing to do is just, get over it. What is d squared y dx squared? It just means the derivative with respect to x of dy dx. Okay, this is what I want to do. How am I going to do this? Well, let's take a step back and just ask how do we do this for some kind of parametric curve? D squared y dx squared of some parametric curve. Well, okay, yeah, so as I just said, it's this, right? It's the derivative with respect to x of dy dx. All right, what does this mean, and how do I actually go about computing it? Both of those are kind of hard. So remember, a parametric curve can be any kind of, insane thing, right? And who knows what it's going to look like. But the sort of the big picture here is that at some kind of point, at some particular t value, I have this tangent line, and the slope of the tangent line is just dy dx. So this is dx, this is dy, and therefore the slope is dy dx. Just kind of repeating what we did earlier. Okay, well, I want to know whether this thing is concave up or concave down. And so maybe down here on the bottom or something, let me just say, now that we know what is concave up. Okay, I said tangent lines lie below the curve, but now that definition's not quite good enough anymore because, it's still pretty good, but because the curve might not even be a function anymore, it's kind of like tangent lines lie, maybe we should revert back to the, sort of the book's definition of concave up, which is that the derivatives are increasing. So I'll say that a arbitrary curve, which is not necessarily a function, will be concave up when the slopes of the tangent lines to the curve are increasing. So that is another increasing, and that says curve. Okay, and a arbitrary curve, which is not necessarily a function, will be concave down when the slopes of the tangent lines to the curve are decreasing. Okay, so the knowledge that I want right now is what is happening to the slope of the tangent line to the curve. But, and I think this is subtle here, when I'm talking about the curve itself, I'm talking about the curve itself, not about the way in which the curve is traced out. As you well know from Pre-Calc C, the same curve can be traced out in an infinite number of different ways. So, for example, if you just give me the curve, just the curve, then, and you point to a particular spot on that curve, I have no idea sort of the speed with which the object is moving along that curve at that point, which direction it's coming from, nothing, none of those things. But whether the curve is concave up or concave down somewhere is independent of the particular parametrization. In other words, whether the curve is kind of bending in a concave up or a concave down way is a property of the curve, not a property of the way in which the curve is traced out. Therefore, it really is the derivative with respect to x that I want. I think that's kind of crucial, right? That the thing which is going to tell me whether the curve is concave up or concave down is this calculation. You take the slope of the tangent line to the curve, and you say what happens to that slope when x changes by a little bit. In other words, scoot x over a tiny little bit in the positive direction. That's what the derivative with respect to x means, right? Increase x by a tiny bit, what happens to dy dx? And the answer is, if you scoot x over by a tiny bit to the right, and the slope has gotten bigger, then it means that the function is concave up. I need you to sort of feel that. And what does it mean to be concave down? What it means for a curve to be concave down somewhere on that curve is that if x changes by a tiny bit in the positive direction and the slope of the tangent line goes down, then the function's concave down, right? Okay, so, all right, with that out of the way, now it becomes just a matter of how to compute this. And you see we're kind of back in our old thing that from the very beginning of class, right? In which I am asking, what is the rate of change of dy dx with respect to x? But the true variable here is t. So this is, I think, very complicated because so x depends on t. Y depends on t. dy dx also depends on t. So the once you have computed dy dx, what you have is now like a kind of a formula, and that formula depends on t. And so you're differentiating dy dx with respect to x. And so the answer is, in order to compute this, we need to know what is the derivative, what is the sort of change in dy dx. This is kind of another, this is not a, well, what is the infinitesimal change in dy dx with respect to an infinitesimal change in x? Which means that once again we're differentiating something with respect to something else where both of them depend on t. And therefore, if this explanation is totally working for you, then hopefully you'll see what to do here, which is to take the derivative with respect to, you need to differentiate dy dx with respect to t over the derivative of x with respect to t. All right, that, for whatever reason, students find this to be very, very hard. There's a level of abstraction involved in this that people just find very difficult. And so I can kind of slow this down a little bit and sort of walk you through it again. So, okay, one more time. Suppose I am, how did I do this? Suppose I am taking the derivative, one second, with respect to x. And it took me many years to reach this particular kind of explanation, but maybe this is now a good explanation. Okay, yeah. Okay, so once again, I'm just giving this same explanation again, right? I want the derivative with respect to x of dy dx. Okay, what is this? Well, what I'm proposing right now is that for our brains to process this, let us mentally realize that dy dx itself is just a function of t. It is something which depends on t. After all, look back at this example, and you'll see that that's exactly what we got, right? Dy dx is something that depends on t. And so it's just another thing that depends on t. Let's call it something. So let's just agree to, temporarily call dy dx z or something like that. In other words, it's just another variable or quantity depending on t. And if dy dx just depends on t, then what we're really doing is we're just taking the derivative with respect to x of this z thing. But the derivative with respect to x of z is dz dx. In other words, this situation is no different from this situation at the beginning of this lecture. I am differentiating z with respect to x, but z and x are both things that depend on t. So for all the same reasons, this is dz dt over dx dt. And of course, what is dz dt? It's just the derivative with respect to t of z. And what is dx dt? Well, if it makes you feel better, you can also write it as the derivative with respect to t of x. And here, I have now, sort of by temporarily calling dy dx z, maybe I've just put it in a form in which it looks exactly like something you already understand, and so this was easy to follow. But anyway, we're done, right? Because now I've sort of proven my point that this is just the derivative with respect to t of dy dx over dx dt. Okay. Whew, hopefully that explanation worked for you. Let's, maybe I needed to pause there for a second for processing. Okay, so this is my lesson on computing this in general. How about now for this particular example? Well, hopefully now you realize that I have this, I suppose I should write what the formula is that we computed. I think it's like 3t squared minus 3 over 2t, I believe, is right. I don't even have it written down, but yeah, that's just right, isn't it? Yeah. So, going back to finish this problem now, if I want the derivative with respect to x of dy dx, it's going to be the derivative with respect to t of dy dx over dx dt. This is the thing that's going to tell us the concavity. And all right, so now I need to differentiate with respect to t this expression, 3t squared minus 3 over 2t. And then that whole thing will be put over dx dt, which is just 2t, I guess. Okay, so continuing, now I just do this, say using the quotient rule. Why not? So what do we get here? Derivative of the top, which is 6t times the bottom 2t minus the top 3t squared minus 3 times the derivative of the bottom, which is 2. The top times the bottom minus the top times the derivative of the bottom all over the bottom squared, but then all of that is over 2t. And all right, when all the dust clears here, what do I end up with? 12t squared minus 6t squared plus 6, I guess, all over... hold on, something maybe went wrong. Sorry, derivative, I'm panicking for a second. Derivative of the top times the bottom minus the top times the derivative of 12t squared minus 6t, I guess this is right, plus 6, sure, all over 8t cubed. Okay, so what do I get here? I get 6t squared plus 6 over 8t cubed, and I guess I can take a 2 out of the top and bottom. So that becomes 3t squared plus 1 over, I don't remember this answer, over 8 over 4t cubed. But I guess this must be the right answer. I hope I'm not making a horrible algebra mistake. 4t cubed. Pause for like 1 second while I, it's very high quality video here. I think this is a video of me doing this from several years ago, and this is kind of annoying, but you could say, hey, Mr. Rose, why didn't you just assign this video? And I really could have. Yeah, that's the right answer. 3t squared plus 3. Okay. So, all right, what's the point of this? I have now concluded that that this d squared y dx squared is indeed 3t squared plus 3 over 4t cubed. Okay, so what? What do I have here? I have a formula which takes as input a time and outputs the second derivative of the curve at the point that the object is at that time. More precisely, I have a function which takes as input a time and outputs for the location on the curve where I am at that time, the rate of change of the slopes of the tangent lines to the curve. Therefore, if I analyze the sign of this expression, and that's easy to do because this numerator is always positive and the denominator is going to change sign at 0 from negative to positive, I can tell you something. And what I can tell you is that for negative t values, the slopes of the tangent lines to the curve are decreasing. And for positive t, which means if the slopes of the tangent lines to the curves are decreasing, then the function must be, the curve must be concave down. And for positive t values, the slopes of the tangent lines to the curve are increasing. And so the curve must be concave up. Okay, so if you want to use the full power of calculus to learn about the shape of your curve, then you also need to compute on what intervals the curve is concave up and concave down. And that actually, in a perfect world, we would have done this first and then at the end sketched this curve. But indeed, you do see, as predicted by this analysis, that my curve is concave down for negative t values and concave up for positive t values. And here we are at time negative infinity, and indeed from time negative infinity to time 0, which is the first half of this fish, the tail and the sort of bottom tail and the top half of the head, that the curve is it's kind of weird. When I use my the curve is concave down, and for positive t values, for the bottom half of the fish head and the top part of the tail, the curve is concave down. So this is indeed the right picture. What's potentially confusing is if you're still watching and you want to have total clarity on this, but potentially also get confused and maybe unconfused, is take some negative t value, like negative 2, where negative 2 are presumably like around here somewhere. No, this would even be like negative 1.5. Okay, so you can't see my cursor when I use the pen, but around negative 1.5, I'm like here, right? And you might be asking, what's happening to the slopes of the tangent lines to the curve here? Didn't you just tell me that the curve is concave down? It is concave down, it looks concave down, that is the right answer. However, as we are actually tracing this fish in this direction, then as we move this way, what's happening to the slopes of the tangent lines to the curves? They're actually going from a negative, this is so hard, they're going from a big negative slope to a small negative slope. And therefore, going from big negative to small positive, you would say that the slopes of the tangent lines are increasing. Okay. However, that is the wrong way, though that is completely true, that's the wrong way of thinking about it. Because when I ask whether the curve itself is concave up or concave down, I abstract away from the particular order in which the curve is being traced out. So I agree to not ask that question. The question I just asked is, what is the rate of change of dy dx with respect to t? But that's not what will tell me the concavity of the curve. What will tell me the concavity of the curve is the rate of change of dy dx with respect to x. In other words, when it comes to predicting the shape of this curve, you have to delete all these red arrows and simply look at the curve itself. And on the curve itself, as x moves by a tiny bit, we now ask, for a tiny change in x, what is the slope of the tangent line to the curve doing? And therefore, scooting over in the positive x direction by a tiny bit results in the slopes of the tangent lines going from a small positive to a small negative. And so indeed, the dy dx is decreasing with respect to x on this parametric curve on negative t intervals, which is what we got here in the calculation, right? That we predicted correctly that the curve was concave down, which is just true, and that prediction comes from asking the right question, which is what is happening to dy dx with respect to a small change in x. Okay, so this is the kind of reason why we put so much time and effort into really understanding the chain rule deeply back in March, because it really is important that you understand, you know, this idea of differentiating with respect to different variables. I think it kind of comes here. All right, this is very hard. So good luck. Hopefully this video was helpful, and hopefully you watched it. Let's stop it now. Woo. Somehow. Oh my god. All right, or not. What? Oh, there we go.